All right, so here we are. We have reached, I think, my favorite topic that is discussed in first semester biochemistry course, and that is enzyme inhibition and enzyme basically activity. So this is a chunk of material that is a little bit more calculation heavy, but all of this can be done with a simple for function or a scientific calculator. There's no need for a programmable calculator, and we won't be using programmable calculators on any exams or anything like that. So with all of that in mind, though, I'd like to go ahead and get into the discussion of enzyme kinetics and reaction kinetics. So enzyme kinetics is the study of the rates of reactions, and enzymes endow cells with remarkable capacity to exert kinetic control over thermodynamic potentiality. Enzymes are the agents of metabolic function, and ultimately what we want to be able to determine is how quickly an enzyme can catalyze a reaction, what affinity that an enzyme has for a given substrate, and then when we talk later on about inhibition, what is the affinity that an enzyme has for that inhibitor? Is it an inhibitor that has, or that an enzyme has very low affinity for, in which case, how good of an inhibitor is it? Or how much of a concern is it? I guess you could also look at it. Ultimately, what these things can tell us are a little bit more about the pathway and the metabolic pathway and movement of resources through an organism. It can tell us about flow through a metabolic pathway, utilization of substrates. Those are the things that we can get from maximum velocity, substrate affinity, and inhibitor affinity. Now, what can we do with that information? Well, we can control and manipulate metabolic events. So when we talk about reaction rates, we are talking about a forward and reverse reaction rate. We're talking about a system that's in equilibrium. So K sub 1 is our rate constant for the forward reaction. K sub minus 1 is the rate constant of the reverse reaction. The rate of the forward reaction is looked at as V sub F, or velocity, final velocity, is equal to the change in concentration of your product, B, over change in time. So how much of B is produced in a time frame. That is equal to negative change in concentration of your reactant in time. So basically, you can look at your reaction velocity as either the creation of your product or the depletion of your reactant, which is what's displayed here. And that ultimately gives you a way of looking at velocity as K sub 1 is, velocity is equal to K sub 1, your forward reaction rate constant, times the concentration of A. The rate is proportional to the concentration of A. K is the proportionality constant, and in this case has the units of inverse time. So velocity is equal to our units for K, which are inverse time. So ultimately your velocity is going to have units of a concentration measurement like millimolar per second. Another one would be something like molar per second. And just as a little bit of a review, that is the same as that right there. And this, of course, is a times, just to rehash a little bit of Gen Chem 1 and old units you maybe haven't thought about for a minute. The rate only depends on the concentration of A, a first order reaction, and first ordered with respect to reactant A. An uncatalyzed reaction, substrate going to a product, is going to have a reaction that looks like this, or a plot that looks like this, where they're looking at final velocity versus substrate concentration. So final velocity is on our y-axis and substrate concentration is on our x-axis. Now, our uncatalyzed reaction, V sub F, is equal to our rate constant times substrate concentration. It's a first order reaction, and our slope is equal to K sub 1. For a catalyzed reaction, things are going to be a little bit different. Why is that? Well, because we have to consider one other component. For an enzyme catalyzed reaction, we have our substrate going to our product, sure, but the difference between the catalyzed and uncatalyzed reactions is we have to concern ourselves or be aware of an enzyme's concentration. And so that's one kind of hidden variable. Now, what is also different is we're looking at the initial velocity, V sub 0, on a y-axis versus substrate concentration on our x-axis. Now, to answer the question, what is the difference between the uncatalyzed and catalyzed reactions? Well, this question is really asking about what's the difference between this plot and this plot right here. Well, this would be a linear plot or linear graph. Whereas these three curves, you can tell that they are, well, they are not linear. These are hyperbolic curves. And where have we heard hyperbolic before? When we were talking about oxygen binding curves. Now, when the substrate concentration is high, so over here, and velocity is not dependent on substrate concentration, rather dependent on the amount of enzyme. So if we look at these three models, or these three different lines, what's changing between the orange, red, and green lines is that our concentration of our enzyme is increasing. So as we increase the enzyme's concentration, then we see our velocity increase. And what's important to notice about that is basically from this point on, where I'm going to label a big X, moving forward, for all of these lines, no matter how you increase the substrate concentration, the velocity is not really going to change. Why is that? Because you have a limiting reactant in each one of these, and that is your enzyme's concentration. Therefore, we must modify the rate equation to include our enzyme. Okay, so that goes back to what is the difference between these graphs. One of which is that your enzyme is a limiting reactant. It is a part of the reaction that you have to consider. So ultimately, we have a pair of folks who came up with this vision or way of looking at kinetics known as Michaelis-Menten kinetics. Does anyone want to take a wild guess as to the last name of the people who came up with these? That's right, Michaelis and Menten. It was Maud Menten, and I can't remember the fellow's name. His first name, his last name was Michaelis. So Maud Menten and I'll say Archibald. I don't think it was, but anyway, what was it? It escapes me at the moment. They came up with this model that looks like this. We are not simply looking at a substrate being converted to a product. Instead, we are looking at an enzyme reacting with a substrate, forming a transition state or intermediate, which is our enzyme substrate complex. Once that enzyme substrate complex is formed, then we can form our P or our product, and we can release our free enzyme. What they came up with as a result of these things was, well, we've got to consider a couple new rate constants. One, K sub 1. That's not our substrate going to our product, but rather our substrate and our enzyme forming this ES complex. K sub 2 is taking our ES complex form, or our formed ES complex, to produce our product and our free enzyme. Now, what's not displayed here is we also have a reverse reaction. We have a reverse rate constant K sub -1, which we've previously seen. This is our enzyme substrate breaking down into the free enzyme and the free substrate. There is also a K sub -2, but that requires our product and our enzyme to go back to the enzyme substrate complex. And this is basically omitted because the equilibrium shifts so far to the right that K sub -2 is essentially negligible. And so it's omitted. Now, the enzyme and substrate associate reversibly to form the ES complex, or our enzyme substrate complex. The product is formed in the second step when ES breaks down to yield E plus P, or P plus E. The organization of E and P, or P and E, does not matter. Now, we have something known as a saturation effect. The system is saturated with a substrate. No effect is seen when the substrate concentration is increased. So you have the saturation effect when basically add more S and rate doesn't change. When substrate concentration is very high, we can go ahead and imagine that all of our free enzyme is in that enzyme substrate complex, which means that our formation of our product, rather than being related to the substrate concentration, is a measure of our K sub minus 2 rate constant times our enzyme substrate complex concentration. So our enzyme velocity is V is equal to K sub 2 times the enzyme substrate complex. The tricky thing about this enzyme substrate complex is this is not something that's experimentally measurable. For a kinetic rate equation to be useful, you must express it in terms that can actually be measured. So the velocity of our product formation is equal to our rate constant times our enzyme substrate complex formation. But if we can't figure out our concentration of our enzyme substrate complex, how can we really come up with this? Now, what we can measure and what we can evaluate is what is our enzyme concentration at a given time, our free enzyme concentration at a given time, and what is our substrate concentration at a given time. So we can use those to ultimately derive a new expression. Using those terms. And this is known as the Michaelis-Menten equation. So using these different terms and times, we come up with this Michaelis-Menten equation. When the enzyme is saturated, the velocity is at its peak. So whenever the enzyme is provided with an infinite amount of our substrate, well, then that enzyme is going to be able to produce the product as fast as it possibly could. It can't do it any faster. Now, when your substrate concentration is very high relative to the Km, all of your enzyme sites are occupied by substrate. So ET, your enzyme concentration at a given time, is equal to your enzyme substrate complex. Now, this term right here, Km, that's something that we're going to get into in just a little while. This is known as the Michaelis-Menten constant. And I'll get a solid definition of that representation for you all in just a moment. But what we can say is that saturation, so whenever our substrate concentration is infinitely high, we have reached our maximum velocity. Our Vmax, the fastest that our enzyme can possibly go, is equal to our K sub 2 times our enzyme concentration at a given time. The enzyme is not always saturated, so velocity at all ranges of substrate concentrations is given by this Michaelis-Menten equation. This equation is very important for y'all to know. This is V sub 0, or your initial velocity, is equal to Vmax times your substrate concentration divided by Km, which is that Michaelis-Menten constant, plus substrate concentration. Therefore, the rate of an enzyme catalyzed reaction, or velocity, is determined by the constant Km and Vmax in the concentration of your substrate. Okay, so what that means is your velocity is determined based on your Km, Vmax, and your substrate concentration. So to use this equation, this Michaelis, okay, I'm going to go off a little bit and give you the explanation as to what a Km is. The Km is a couple of things. One thing that it is a measure of affinity for your substrate, or your enzyme's affinity for your substrate. Another thing that your Km is it is the, actually I'm going to bounce back a couple of slides. I'm going to erase all of this. And for the purposes of this exercise, let's just ignore Ignore the bottom two lines. And I mentioned that this was a hyperbolic curve. URB. As a hyperbolic curve, or my question is, when have we previously seen a hyperbolic curve? And I mentioned this earlier. This looks like an O2 binding curve for myoglobin. And when we look at the O2 binding curve for myoglobin, if you remember, we had our y-axis, which was percent saturation. So kind of it was a measure from 0 to 100. It was a lowest possible saturation to highest possible saturation. The highest possible was 100%. So think about that the way that you think about velocity in which an enzyme is going to catalyze a reaction. It's got a certain speed. We don't care about the units or anything like that, but an enzyme is going to be able to produce a product, and it's going to be able to produce a product the fastest that it can possibly produce that product is 100% of its velocity. Therefore, that would be equivalent to 100% velocity equal to what's known as a Vmax. So our y-axis here is similar to an O2 binding curve's y-axis. We measured basically how fast can an enzyme possibly catalyze this reaction. And we came up with the term Vmax, which is analogous to when an oxygen binding protein is completely saturated. It's doing everything that it possibly can to bind oxygen, just as an enzyme is doing everything it possibly can to produce a product. So we have on our y-axis a v sub 0, or a velocity. Now on our x-axis, if you think about an oxygen binding curve, what do we have on our x-axis? We had the partial pressure of O2. And the partial pressure of O2 gave us a measure of, well, when is this protein saturated with O2? Was it 5 torr, 10, 15, 20, 25, whatever? Some quantity, basically an oxygen concentration, that protein was saturated. And what we used to compare oxygen binding proteins was we looked at, well, their P50. What concentration got that protein to be saturated, or 50% saturated? And so what we would do is we would take our y-axis and we would cut it in half, and then we would do the dots to come up with the coordinates, and we would say, aha, well, there it is, 4. 4 torr gets our protein 50% saturated. Well, when we're talking about an enzyme, we're effectively doing the same thing. The P50 is not it's not a P50, but it's the same position on the graph. It is known, however, as a KM. Now, if you remember your P50, what that gave you, and actually, you know what I'm going to do? I'm just going to draw an O2 binding curve and a Michaelis-Menten curve. At this point in time, you can't distinguish these graphs from one another. However, whenever I put my y-axis labels on, then you can. O2% saturation. We have a 100% saturated. We have a 50% saturated. And this would be, let's say, 6 torr. Well, when we talk about an enzyme catalyzed reaction, we have the V max. Then we also have what's half of V max. That is our Km, which let's say that it's 2.5 millimolar. And I just made that number up. Essentially, what's important to understand is the similarities between these graphs. If you remember, when P50 goes down, what does that mean about that oxygen binding protein's affinity for oxygen? Well, if the P50 goes down, the affinity goes up. If the P50, on the other hand, goes up, what happens to your affinity? That goes down. So similarly, if your Km goes down, that enzyme's affinity for that substrate, what do you think happens? Goes up. Km goes up. What does that mean for the enzyme's affinity for that substrate? That goes down. So if you have a good understanding of an oxygen binding curve, this Michaelis-Menten curve is effectively going to look almost the exact same. Your Km is analogous to your P50. If the P50 goes down, that's the same thing as if your Km goes down. Your affinity goes up. So I hope that was helpful. Now, with that in mind, let's look at an example problem. When your substrate concentration is equal, or when your substrate concentration is equal to 5 km, let's go ahead and copy this equation. V sub 0 equals V max times substrate concentration over Km plus substrate concentration. This says when your substrate concentration, this should be bracketed, is equal to 5 km, what is your ratio of your initial velocity to your maximum velocity? Now, this question is asking you basically to do a little bit of algebra. And what it's asking is, if you took this equation, V sub 0 equals V max times substrate concentration over Km plus substrate concentration, how can you manipulate this to get this right here, V sub 0 over V max? What we need to do is get V max into the numerator. How are we going to do that? Well, before we get to that, I mean, that's kind of our goal and that's our objective. What this also tells us is that our substrate concentration is 5 times our Km. So what I'm going to do is substitute that substrate concentration, or substitute that 5 km for our substrate concentration. So I'm going to rewrite this equation as V sub 0 equals V max times 5 km over Km plus 5 km. Now what we can do with this is we can combine different components. We could rewrite this now as V sub 0. Actually, I'm just going to go ahead and say this is equal to V max times 5 km divided by 1 km plus 5 km equals 6 km. What I'm also going to be able to do is take out the common variable. There's Km present in both the numerator and the denominator. So I'm going to eliminate this and eliminate this. And so now what I've got is V sub 0 is equal to 5 V max over 6. And you know what? If I multiply each one of these by 1 over V max, and what I mean each side of this, times 1 over V max, I will end up with V max being omitted, V sub 0 over V max is equal to 5 over 6. So what is my ratio of my velocity to my Vmax? It's 5/6. And this kind of goes through the explanation of that using, that's that. And that's what I ended up with. I removed that Km. I ended up with Vmax, and there we go. Now, another question. Go ahead and erase all this. I hope that you know that you can pause and look at that. Now, using the same equation, this goes on to say, what relationship exists between Km and substrate concentration when an enzyme catalyzed reaction proceeds at 75% of the Vmax? So you got to take some things out of this question. An enzyme catalyzed reaction proceeds at 75% of Vmax. Essentially what that's saying is you are at 0.75 times Vmax, which that is your velocity. So you could look at this and say, all right, well, using the equation V sub 0 equals Vmax times substrate concentration over Km plus substrate concentration, substituting in 0.75 Vmax equals Vmax times substrate concentration over Km plus substrate concentration. What we can do right off the bat is remove our Vmax component. And so then we end up with, let me erase this. We end up with 0.75 Vmax over Vmax is equal to substrate concentration divided by substrate concentration plus Km. So the way that I had this set up, 0.75 Vmax equals Vmax essentially what was done here was you divide each side by Vmax, and you're able to eliminate that Vmax. And so that's why we arrive at 0.75. Then there's another little step of algebra. 0.75 equals substrate concentration over Km plus substrate concentration. Now, what you can do is multiply each side by what's in the denominator. Km plus substrate concentration. On this side, boom, that's gone. And then over here, Km plus substrate concentration. That's where we get this. I'm going to erase the work that I've done. And now what we're left with is distributing this 0.75. So we get 0.75 Km plus 0.75 substrate concentration equals substrate concentration. This substrate concentration that's indicated right there on the right-hand side of the equation, that's the same as one substrate concentration. So minus 0.75 substrate concentration from each side gives us 0.75 Km equals 0.25 substrate concentration. Then what we can do is we can divide each side by 0.25. And we can say that, well, 3 times Km equals our substrate concentration. So essentially, this second equation says when your enzyme is going 75 times or 75% of its maximum speed. So what is the concentration of your substrate whenever that's the case? And the answer is your substrate's concentration is 3 times your Km. Okay, so let's just review this term, Km. Your Km is the concentration where your enzyme is at half of its maximum velocity. Okay, so if that is, I'm going to jump back a little bit for this slide, where I put it together right here. This equation right here. This is my Vmax. This is my Km. 75% of my Vmax, I'm going to switch colors on my pen just for the sake of organization. Let's go with blue. 75% of Vmax is right here. Now, the question that we were just working through is what substrate concentration will get you to 75% of your Vmax? And the answer was 3 times your Km. So essentially, 7.5 millimolar for this example. Remember, I just arbitrarily came up with this number for this Km. 3 times your Km, or 7.5 millimolar of your substrate, gets you to 75% of your Vmax. So people have a tendency to look at this and say, oh, well, if I'm at 2 times my Km, then I'm at my maximum velocity. That's not the case. If you triple the concentration of your substrate, or sorry, if you take the Km of your substrate when substrate equals Km, you're at half of Vmax, 1/2 Vmax. Okay. So then what people have a tendency to think is, oh, well, if I double my substrate concentration, then I'm at Vmax. You're not. If you say your substrate concentration is 3 times your Km, you're at 75% of your Vmax. So in order to get closer and closer to your maximum velocity, you have to continue increasing the substrate concentration. Now, these two practice problems, I think, are great ways to look at substrate concentration and Km. And you should expect a question like that, or like those two. Now, this just shows how I wanted to compare the Michaelis-Menten equation and plot of the Michaelis-Menten equation with an oxygen binding curve for myoglobin. So some important conclusions of the Michaelis-Menten kinetics and of that equation is when your substrate concentration is equal to your Km, the equation reduces down to your velocity is half of your Vmax. So when your substrate concentration is considerably greater than your Km, the equation reduces to your velocity is equal to your Vmax. When the substrate concentration is considerably lower than your Km, it reduces down to V, or your velocity is equal to a ratio between your Vmax and your Km times your substrate concentration. So the Michaelis-Menten equation is very important for understanding enzyme kinetics and visualizing this graph. And I think that, again, understanding an oxygen binding curve, if that curve moves to the left or if it moves to the right, what does that mean for your Km? In addition to that, I always like to ask the question, what are the units of Km? Well, they're going to be a concentration. They might be millimolar, they might be nanomolar, they might be molar. It just depends on that enzyme. And that was also a measure of your enzyme's affinity for that substrate. Okay, so we'll take a little break.